Question 2 starts off with a distance matrix, so you can read all the information yourself, but basically this is just a distance matrix, and it's not directed, which we can tell because if we look along the main diagonal here, you can see the entrances are symmetrical about the main diagonal, so 42, 42, 20, 20, and so on. So we don't have to worry about the direction, so we don't have to worry about which way we read these, but yeah, so basically in part 1, we're just told to draw a graph using this information, a weighted graph. So I'm just going to make this a little bit smaller, and I'm going to come down here. I have all the nodes drawn out already, but it doesn't actually matter how you draw them out. I've just drawn them out in a way that'll work out nicely because I've prepared this in advance. So firstly, we can see that we have A to B here, which is going to be 42. So we'll connect an edge from A to B, and that'll be 42. And I'll just put an underline there just so we know we've done it. Then we look at A to C when we have 33. So let's do 33 here. And each of these are in milliseconds, but we won't write it on this to clog, because that'll just clog it up. But if we're giving a final answer, we'll have to make sure to give it in milliseconds, as the question says. Anyway, that's all of them for A. Then if we look at row B, well, we already have B to A. A to B is the same as B to A. So in reality, we actually don't have to worry about anything on the bottom side of this main diagonal, because as you can see, it's all the same entries as the other side. So we only really have to worry about this top side. It's kind of a trick that I like to use. So if we look at B, B to C is going to be 20. So B to C, we do 20. Then I'm just going to put a little underline to show that we're done. B to D is 54. B to D, we have 54. And that's it for B. Now if we look at C, we have C to E, because the other ones on the other side, we've already done them. We've done C to A and C to B. So we're going to look at C to E is 105. So C to E, that'll be 105. Then we have C to F, which is 78. Then I'll just underline that. Now we're done with C. Then we look at D. D to E is 29. So D to E, it's 29. And then D to G is 94. So we can do this, 94. Then we're moving on to E. E to F is 41. So just cross that out. E to F, 41. E to G is 49. E to G, 49. And then finally, we're on row F. F to G is 71. Oops, it's a black line. It's going to be 71. And that's the entire graph. And you can see everything that we didn't do on this side of the diagonal, we already did on the other side because they're all the same numbers. In part 2, we're asked to calculate the shortest time for a message to travel through from computer A to G. List the computers that it travels through in order and name the algorithm you used and show your work. So of course we're going to use Dijkstra's algorithm. Technically another optimal path is Bellman's algorithm or dynamic programming, but we don't see an easy way to break this up into stages, so we'll use Dijkstra's algorithm. So we'll name it Dijkstra's algorithm. And they actually give you 3 marks just for naming the algorithm, which is quite generous, but yeah. So it's very important to say that you're using Dijkstra's algorithm. Okay, and then I know a lot of people do it with boxes, and it's done with boxes in the book, but applied maths is quite a time-tight exam, so I don't usually use boxes. Usually I'll do it this way, then I'm about to show you now. So, and this will show our relevant supporting work. So this is from A to G. So what we'll do is we'll start at A. Actually no, it's fine the way it is. So we'll start at A, and I'll put a box around it, just say that we're working on A, and I'll scribble it in because we're done with A technically. Now we're going to look at everything that's beside A, which is C and B, and we're just going to put boxes around them. And then we're going to look at the distances to get to A from those boxes. So for C, it's going to be a distance of 33 to get to A, and for B, it's a distance of 42 to get to A. Then we choose which one is better out of our boxes that haven't been completed yet. Well, it's obviously C, so we color in C to say that we're done with it. Then we draw an arrow back to A. And now we look at everything that's connected to C. So we also have E, we have F, and we also have B. And now we calculate how long does it take to get from these nodes to A going through C. So if we were to go from B through C to A, we have this 33 from C to A plus the 20 to B. That'll be 55 if we were to go through C. For E, we'd have 105 plus 33, which is 138 if we were to go through C. So it's important to write the letters so that you know which node you're going through. And then finally for F, we'd have 33 plus 78, which is 111. And that's also going through C. Then we see which one out of our partially completed is the smallest. Well, it's going to be this 42 through B. So we'll put a cross through this to show, because we have multiple options for B, we're not going to use the one going through C, we're just going to use the one going straight to A. So yeah, we're going to just draw an arrow. This should say A, but it doesn't really matter. Just to say that we're going through A, or we're going to A. And that's the one we ended up using, and now we're done with B, so we color it in. Then we look at what's connected to B. Well, D is the only one that's connected that's not done yet. If we were to go 2A through B with D, then we'd have 54 plus 42, which is going to be 96 going through B. Then we look at all of these. What's the smallest? Well, it's actually D with the 96 going through B. And that's why it's good that we write the letter, because we know that we're going to draw this arrow going to B. And then we put a box to everything that's connected to D. So connected to D is G and E. B is 2, but B is already done. Then we look at both of them. So if we were to go from G, going from G all the way to A, going through D, because remember we're looking at D, that's the one that we last did, we'd have the 96 to get from D to A, plus the 94, giving you 190 if we were to go through D. And then for E, we'd have the 29 plus the 96, which is going to give us 125 if we were to go through D. And that's why we keep our options open, because as you can see here, if we were to only consider the C, the D is actually better than that. So it's good that we consider the C or the D as well, instead of just the C. Now we look at all the ones that are partially complete with a box around them, and the smallest one is this F here, which with 111. So I'll color that in, and that's going to be going through C, so we'll draw an arrow. Then we look at everything connected to F, and we have E and G. So if we were to go from G to A going through F, we'd have the 71 plus this 111, giving us 182 if we were to go through F. And then for E, because remember E is also connected to F, if we were to go from E to A going through F, we'd have 41 plus this 111, which gives us 152. So I'm running out of space. 152 through F. What's the smallest one on our diagram? Well, it's obviously this 125 for the E. So I'll color this in, and this is why it's good to write down the letters. Where's this 125? This is going to D. So we'll draw an arrow going to D. We'll cross out the other two to show that we're not using them. The only one that's left is G, and that's connected to E. So how can we get 2A through E from G? So we're going from G to A, and we're going through E, because that's the one that we most recently did. We'll do 49 plus 125. 49 to get from G to E, 125 to get from E back to the start. We'll have 49 plus 125, gives us 174 going through E. And as you can see, that's our best option yet for G, which is why we didn't just choose one of these, even though we already found it, or one of the other two. So this is the only option left, and we're going to use the 174 going through E. So now G is done, so we can color it in, and then we're going through E. So we're done doing the algorithm, and now it says list the computers that the message traveled through in order. Well, we actually have this in reverse, because we started, that's kind of how Dijkstra's algorithm works, so we just have to reverse it. So if we just start at G and follow the path, so we're going to go from G to E, so G to E, and then from E to D, from D to B, and then from there to A. But of course we're starting at A, so it says from A to G. And yeah, I just followed the path here. G to E, E to D, D to B, B to A. We can just reverse that to go from A to G. So we'd have A to B to D to E to G. Oops, didn't draw the arrow there. I'll bring this over under the rest of our work. And the shortest time for a message to travel through, well, we see here, to get to G in the end, it took 174. So I'll write down 174. I might just make it super clear. You might write shortest time. Oops, shortest time equals 174. And then just in case, they don't usually mind, but it's still good to be safe. It tells us that each of the numbers are in milliseconds. The time's in milliseconds here. So we will write 174 milliseconds. And that's the end of part 2. So part B is a difference equations question. So we're told about this computer network. Message travels from one to the other. And then every time it travels, the number of errors increases by 15%. And then C errors are corrected each time. And the number of computers it travels is counted using the number n. It starts at 0, And we're basically using this difference equation, that the number of errors in the n plus 1th term is 1.15 times the number of errors, because it increases by 15%, taking away the number of errors that are corrected. And then we're modeling this with this difference equation, and we know that there are 101 errors when it leaves the computer, so E0 is 101. We're told to just solve this difference equation, not differential equation. So basically, the way I like to do these is kind of with the same method every time, the second order inhomogeneous method. So the first thing we always do is we find the complementary solution. Complementary. And what we do for that is we just ignore everything that's not an en term. So this c has nothing to do with the en, so I'm going to ignore that for a second. I'm just going to have that en plus 1 equals 1.15 en. Now we find the characteristic equation, which we can do by replacing these ens with x's or ors or whatever you want to call it. Since this en plus 1 is one term ahead, we'll call that the x, which is the highest power, equals 1.15 times technically x to the power of 0, since this is another one down, but x to the power of 0 is just 1, so we just have x equals 1.15. That means that our complementary solution, which I'll write as en complementary, is going to be of the form, this is just one of the theorems on the course, 1.15 to the power of n times some constant a. And that's our complementary solution. And then we also need to find our particular solution. So since in the complementary solution, particular, that's how you spell it. Since in our complementary solution we ignored everything that wasn't an en, we're kind of doing the opposite here. We're going to ignore everything that isn't that is an en. So basically we just have some constant at the end. And if the extra term is just a constant, that means that our particular solution, p for particular, will be of the form just some constant, which I'm going to call d, just not so we don't confuse it with that c. And then we need to sub this back into our original equation to figure out what d is, but we can't actually do that yet because we don't know what en plus 1 is in our particular solution. So we'll have to just do that, en plus 1 to the power of p, not to the power of p, that's just for particular, to show that it's particular, our particular solution. When we change it to n plus 1, the constant stays constant, it doesn't change, it's still just going to be d. So sub that back into our original equation, we have en plus 1, which I'm just going to replace with d for our particular solution, equals 1.15 times en, which is also just d, minus c. We can bring the d's to the other side, and we get minus 0.15d equals minus c, or in other words, we get that d is equal to c divided by 0.15. So that's our d, and that means that our particular solution, our enp, which was just d, is going to be c over 0.15. You could do stuff with fractions, but it gets very messy, so I'm just going to leave it like that. Now our final solution for en will be the sum of our particular and complementary solution. So we'll have a times 1.15 to the power of n plus c over 0.15. Yeah. Oops. 5. Why can't I draw 5? There we go. And then we're told that to find an expression for en in terms of n and c, well, we have an a here, and we need to get rid of that a. How can we do that? Well, we're told that there's an initial condition that E0 is 101. So we'll just plug that in. So E0 will be equal to 101, which is the same as replacing everything in the equation with a 0. So we get a times 1.15 to the 0 is just 0, plus c over 0.15, which means that a is equal to 101 minus c over 0.15. So finally, now we know what a is, and we can replace it with something that has c in it. Now the en will be a, and a is just 101 minus c over 0.15 multiplied by 1.15 to the power of n plus c over 0.15. And that's it. You can expand out this bracket if you want, and then factor out the c over 0.015 or 0.15. 0.15. You can do that if you want. You don't have to, though. You can leave it like this, and it's no problem. Then in part 2, we're told that it's found that the message contains 0 errors once it gets to the 21st computer. E21 is 0. Then we're told to calculate c. We get that so we can just say that e is 21. It's going to be 0. And that's just the same. We're going to replace all the n's with the 21. So we're going to have 101 minus c over 0.15 times 1.15 to the power of 21 plus c over 0.15. Now to solve for c, we're going to have to expand out this bracket. So we'll get 0 equals 101 times 1.15 to the 21 minus C, it should be capital C really, I think, C times 1.15 to the 21 all over 0.15 plus C over 0.15. We can bring the constant over to the other side and we'll get minus 101 times 1.15 to the 21 equals, and then we'll factor out a C because we're trying to get that, C times minus 1.15 to the power of 21. Just kind of show that the minus is outside there. Not that it makes a difference in this particular case, because it's an odd power. And then we'll have plus 1 over 0.15. Since they have the same denominator, we don't even have to write the 0.15 twice. We can just combine them into 1, like that. And then finally, to get C by itself, again, you don't have to do it the way I'm doing. You can kind of work it out as you go. I just like to leave it as it is and then put it all into the calculator at once at the end. So just dividing by this big bracket thing, we get that C is equal to this big thing. When you do this, you will get that C is equal to 16.000, and then to the closest, there's a couple of decimals, but to the closest whole number, it's obviously just 16. That's our answer for C. Finally, we're asked to model this using a differential equation, dE dN, rate of change with E with respect to N in terms of E and C. So I'm going to copy down this original question, just so that we can kind of have a look at it a bit more easily. Kind of the words that they use, and we can kind of figure out a differential equation. So I highlighted two important things earlier, but I forgot to copy them down. Is that the number of errors increases by 15% as it travels each time it travels from one computer to the next. And C errors are corrected every time the message travels. And we can kind of use our difference equation here to help. So basically what it's saying is that the next term is 1.15 times the previous term, the previous number of errors. So that's just an increase of 1.15 minus the number of errors corrected. So it's pretty similar if we're doing a differential equation. The rate at which E is changing, the errors with respect to N, is... it's not 1.15 times. The rate at which it's changing actually is we're getting 0.15 times more errors, and then we're taking away C errors each time. And that's the differential equation that models it. Now, the reason it's not 1.15 like above is because this 1.15, the real reason that is because that's En plus 1 equals, the technical long way of writing it, it's going to be En, the previous number, plus 0.15 En. So basically, we're taking the previous number of errors we had, and we're adding on 15% to that, and then we're taking away C. Now, obviously, when we're talking about the rate at which it's changing, we don't care, we're not adding, we don't have the previous number of errors we have. All we care about is how much it's changing by, and how much it's changing by is just 15%, which is why we just have the 0.15 and not the whole 1.15. And that's it for question 2.